Hi, it's time for another math easy solution. Time to discuss another derivatives application and now look at compressibility. This is basically a pretty interesting topic in my calculus book, so I wanted to share it here. So one of the quantities of interest in thermodynamics is compressibility, and this is basically means that if a given substance is kept at a constant temperature right here, then its volume just depends on the pressure right here. So you could just think about something like this: a cylinder, and then basically as you apply pressure, the volume's going to change. It's actually going to decrease. So if you consider the rate of change of volume with respect to pressure, because we're keeping it at a constant temperature, the higher the temperature, the volume expands. But in this case, if we have the same temperature, so it's not dependent on it, then basically if we just consider the rate of volume change with pressure, then the derivative dV over dP, or the derivative with respect to pressure, as basically as the pressure increases, volume decreases here. So if you're applying pressure right here, you're going to be getting a smaller cylinder. So it's going to be, volume is going to be decreasing right here. So it's going to decrease whatever you're applying right there. Or in other words, basically if you increase pressure, then you're going to obviously decrease the volume. And basically the compressibility is defined by introducing a minus sign and dividing this derivative by volume to get it in terms of a unit volume. And we put the minus sign just so that we get a positive value for compressibility when we increase pressure. Yeah, so the definition of it, but in this case we'll put this isothermal in there, isothermal compressibility. This just means iso, or one temperature. Here thermal is representing temperature. So at one temperature, or this constant temperature, the compressibility is defined as, well, -1 divided by v, so we divided by the volume, and then we just multiplied by the rate of volume change with temperature with pressure. And this is given the Greek symbol beta, so this is for compressibility. And thus, if you were to write the definition out, it basically this beta measures how fast per unit volume the volume of a substance decreases at the pressure as the pressure on it increases at constant temperature. And the reason we have this per unit volume is just so if you have a giant volume or whatever, you're obviously going to be compressing really fast, and it would be a large number, but then it might be compressing slower than if you had a smaller volume, but because you're going to be dealing with smaller numbers. But then this is just to kind of get a percentage or a ratio out of it, so that it's easier to compare with different size volumes. Okay, so now to help illustrate the compressibility, I'm going to go over an example here. Basically, if the volume V, which is in cubic meters, of a sample of air at 25 degrees Celsius was found to be related to the pressure P, which is in kilopascals, or kPa, by the equation V equals to 5.3 divided by P. Now the question is, determine the compressibility of the air at a pressure of 50 kPa, or basically P equals 50 right here. So P equals 50 kPa, and we know that the equation for compressibility is just beta is equal to -1 over V dV over dP right here. So we know the initial volume here, this volume is just V is equal to 5.3 divided by 50. But if you plug this into the calculator, we get 0.106 right here. So that's or this is meters cubed. And now we need to determine the rate of change of the volume per versus pressure. So we could just take the derivative of this function right here. That's just dV over dP. So we get V is equal to 5.3 divided by P. So now we take the derivative. So V prime equals to dV over dP. And now using our derivative rules, this is just this could be written as 5.3. This is a power function times P to the -1. So if you recall power rules for derivative, you just put the -1 down, and then 5.3, so multiplied by -1 here, and then this we -1, so it's gonna be P P -2. It's power -2, or this just equals to -5.3 divided by P to the power of 2. And now if we were to plug in basically at because this one here we're looking at temperature of 50, so the derivative of V prime at 50, this equals to -5.3 divided by 50 squared. And this one, if you plug into the calculator, we will get negative 0.00212. This is going to be meters cubed over kPa. And now basically we can solve for the compressibility, so this beta just equals 2, whatever this is, so equal to negative, and then that's 1 over v, so we 0.106, we just go, this is going to be 0.106, and we have a negative right here, 0.00212, and again the units here, this is meters cubed per kPa. And this one is kPa, meters cubed. So that's meters cubed. And if you were to plug this in the calculator, the negatives cancel, and we'll be left with 0.02 right here. And then the units are going to be, well, meters cubed per kPa. This is the way my calculus book writes it, per unit volume right here. Even though these would cancel out, but they just put this here just to show that it is like a ratio or per unit volume right here. So this is the answer. Well, anyways, hopefully you learned from this example. That's all for today. You could always remember, you could always download these exact notes in the Dropbox link below, and hopefully learn basically how you could the derivative could be used to could be applied in compressibility, thermodynamics, in my earlier videos, like in chemistry and in electricity, etc. Anyways, that's all for today, and yeah, hopefully you enjoyed, and stay tuned for another math easy solution.